Hello? All right. I'm hoping this works. OK, so yes, Patrick introduced me, and I'll be giving a talk on understanding the internals of Spark. OK, so the goal of this talk is to understand how Spark runs a program that you've written. But the focus is actually going to be on sort of this getting this understanding to look at performance, how your program runs, how your program executes performantly. OK, so I like to think that there are three major core components of the core of Spark. And these are the execution model, which is how we actually execute your RDD, your program rather. The shuffle, which is really part of the execution model, but what the shuffle means is how we move your data across the network in an all-to-all communication. This is the same thing as the shuffle and map reduce. We try to avoid this whenever possible, but it's important to understand what it means to do a shuffle and why it's expensive and how we can reduce the expense. And finally, we all know that Spark is great for caching stuff in memory explicitly. That's a totally separate part by itself. So I'd like to spend about 15 minutes on each of these. Unfortunately, this is a 30-minute talk, so I'm going to take off caching. Why? Well, it's my talk. I said so. OK, so OK, so let's talk about the execution model. So first, this is getting a little iffy. OK, so first, the idea is why understand the internals at all? And as I said, we're going to go take it from a point of view of performance, understanding your program in order to understand the performance of it. To take an example outside of Spark entirely, let's say I'm on a single-threaded program, and I have an array of like integers or something. Sort of you know, and I know, that if I sequentially iterate through this list, it'll be much more performant than if I randomly access the list. And sort of that's not inherently obvious, but because we understand how caches work, we know that sequential access is better. And so in the same way, you might write a program and you think you know how it works, but really because of how Spark is working underneath, you might not get the exact performance you expect. OK, so that's the idea. That's why we should understand how Spark works. And so this is going to be an example that we're going to use throughout the talk as sort of a vehicle for understanding Spark. OK, and so let's just go through what this example is. The idea of this example is we have a bunch of names in HDFS, and we want to find the number of distinct names and group them by the first letter. OK, so like how many distinct names in my data start with the letter A? All right, so just as an example, we have three names, let's say Ahir, Pat, and Andy. And then the first thing we do is we make a pair of them. We take the first letter, comma, the name. Spark inherently interprets this as a key value pair. So this is the key A with Ahir, P with Pat. By the way, I tried to do Patrick first, but I stuck with Pat instead, who gave the first talk, because it's shorter than it fit on the slides. And then we do a group by key. And yeah, no problem. And then we do a group by key where we rearrange the data such that all of the data for the single key is with the same data. So we have A with Ahir and Andy, and P with Pat. OK, and it's sort of a list or something. And then we take we map values. So the value is this sort of list for each letter. And we first take it to set. And this is important, because I said the distinct names. So what this will do is it'll actually build a set in memory for each letter. And if we had duplicates, they would now be removed. But in this case, there were no duplicates, so there's no real difference. And then we take the size of that set. And so now we know that there were two distinct names starting with A and one starting with P. And we just collect that back to the driver. All right, so that's just the example program we're going to work with. OK, and so it turns out that this isn't a very well-written program. And it may not be entirely inherent why. Additionally, some of the problems with the code that we've written is actually not even on the slide. It's about the data that we're working with and the cluster that we're working with. OK, so let's try to figure out sort of what's going to go wrong when we try to execute this. So first of all, how do we execute this? And I'm going to do this very high level first, and then we'll go through in more detail. So first, we create a directed acyclic graph of RDDs, where an RDD is a sort of partition data set to represent the actual computation. So this is how we represent the computation. Then we create a logical execution plan. How can we possibly execute this directed acyclic graph, and how can we execute it efficiently? And finally, we take that logical plan and make individual tasks and send those to the cluster. OK, so what did all that mean? Well, so the first step is to create the RDDs. And fortunately, you've done this for us. It's very nice of you that you've created the RDDs. You see what all this is each line of the code, except I put it in a box and put an arrow to the next one. All right, this is our RDDs. It was very hard. This is what Spark does internally. It has a box generator and an arrow. And then, OK, so the second step, not the second step, I'm sorry. I'm just going to coalesce this. This is the same thing. You see, we take our Hadoop RDD, which loads the data. We map over to create pairs. We group by key. we take each key, we map values to find the number of distinct elements, and then we finally collect it. Okay, so that's just a reduced version. So now that we have this, we know what the program is and we have a representation of it, how do we execute it? And the idea isn't just, the hard part isn't how to execute it. We did that in the first slide, right, where we showed you, oh, here's how you just go through it and then take the map and all that. The question is, how do we execute it efficiently? And the goal to executing efficiently is to pipeline as much as possible. And what I mean by pipeline is to sort of fuse operations together so that we don't get like costs of like going over the data multiple times or having a lot of overhead for each operation. So just to go through an example, the same example, we have a here, and if we can pipeline, that means we immediately take a here and do the map. We generate a comma here. And then we take the next item and do the map again, et cetera. Okay, so the point is that we've sort of fused these operations, the Hadoop RDD and the map, into one, and such that it's effectively like we take a function call, or we get the I here, and then we take the result of that and immediately pass it into another function call. So that the overhead of multiple operations that are pipelinable is extremely small. It's basically like one function followed by another. All right. And so the question is, when can we pipeline this? It's awesome when we can pipeline stuff. So when is it possible? And it's possible until you can keep pipelining until you need to reorganize the data. All right. So you see the next thing we need to do. Well, okay. Let me rephrase that one other way. Another way to think about needing to reorganize the data is how we generate the result. So when the result can be generated independent of any other data, then we can pipeline. Okay, that's sort of a little bit loosey-goosey, but that's approximately it. So if we take a look at like a comma I here, a comma I here doesn't care about pat. It doesn't need to know about pat in order to be generated, and therefore it can just be done in sort of its own little world. And that's sort of the ideal situation. But in the next case, you see that we have to do the group by, we have to reorganize all of the data such that a here and Andy are in the same place, so they can be grouped into the same key. And so this we can't pipeline past. All right. And so what we're going to do is we're going to make the first two operations into something called a stage. And a stage is basically just a super operation. It's just like a merged operation where we've just like fused these together, we weld them together, and we just run one and the other like together. Okay. After that, we just do this again. We try to pipeline as much as possible, and it turns out after this, we can actually pipeline. We can take the result of this groupBy, take the first element of that, map values it, and okay, the collect is a little bit weird. Let's kind of ignore that. It's not really an RDD. It's really an operation. But so let's say we can pipeline that too, which we can. It's just maybe not clear why. And then we take the P and the pat, and we do the same thing. Okay, so the second part is another stage. So it's another fused operation, which we can group them all together into one super operation called a stage. All right, now that we have our beautiful stages laid out like this, the idea is we have to now execute it. And so we have to schedule tasks to run this. And so what is it? So we split each stage into a set of tasks. And a task is simply data plus computation that we can just ship to a node and have it run it. I'll give an example in a second. And the idea is that we have to execute all of the tasks within one stage. We have to complete the first stage before we can start the second stage. All right. So here's our example. We have our computation. So our computation, right, is the super operation, this fused stage on the left, which is stage one. We'll start with stage one because we have to execute it first. And our data on the right. And our data is just 4 HDFS files, 4 blocks, okay? And so a task is simply grouping these together. We take one, like the first block, group it with computation, second one, third one, and fourth. All right, so now we have 4 tasks. To look at this in a slightly different way, a task is just like this bundle of work. It's this bundle of work that says, hey, load HDFS block 0 and do this computation overhead on it. Okay, and then so we can just send this little task, this little closure, off to a machine and have it execute it, right? It's totally independent of anything else, et cetera. So we have 4 of these tasks. All right, so now that we have our nice little tasks, we have to actually execute them. So this picture is showing a cluster. So this is a Spark cluster of 3 nodes. For the simplicity of this example, we'll say each node only has 1 core, but it's very easy to see how it would work if you had more. We also see that we have HDFS on the left here. Yeah, left. It's always hard up here. So we have HDFS on the left with some set of blocks that are distributed among it. And then we have time, and so the rest of it's going to be time. It's going to be how we execute the actual query. Okay. And so we start at time 0, and then the first task comes in, and we see that the first task is talking about block 0. And so we first look at where is block 0, because we want to schedule this task locally. And we see that block 0 is on the first node, so we just schedule it there. And then a very small amount of time later, the next task comes in. It's a very small amount of time because these tasks are being scheduled from one thread on the driver program, if you recall your Spark. But it's a very small amount of time later, we schedule task 2, or task 1. And so we're going to take task 1, and we're going to put it on the second node, because it's also local there. Task 3 comes in, and we see that it could be either on the second or the third node. In this case, we'll put it on the third node because it's the only one that's free. All right, and so time progresses, obviously. This is all pretty obvious, right? So the time progresses, and then task 1 finishes. Luckily, task 0 finishes, and now we have a free machine again. And so now we have room to execute this fourth and final task. And fortunately, this task is actually local to the first node. If it weren't local to the first node, we might actually wait to schedule it, because we do try to schedule locally through a process called delay scheduling. But that's not relevant here, fortunately, because I don't have time to explain it. So we put that, we put that on the first node, and it's going to execute beautifully because it's running locally. It doesn't have to transfer any data. And then soon after, it finishes. Now, we'll note that one thing sort of went wrong here. If you look at sort of the second half of this computation, approximately only one node was executed. Anything. So like, it was like we didn't have a cluster. We had a single machine. So this happened because we happened to have 4 tasks of approximately equal length and 3 machines. All right. So clearly, we didn't have a good alignment of tasks. So we'll come back to it. Keep that in the back of your mind. But after we've executed these 4 tasks, we've completed the first stage. All right. And now let's talk about how to get to the second stage. So for the second stage, you'll remember we have this groupBy. And in order to do this groupBy, what we need to do is we need to shuffle. All right, this is where the shuffle comes in. We need to rearrange all the data such that all of the data that has the first letter A goes to the same place. All right, and so you've probably seen a picture like this on the right. It's really hard. I was getting back up. All right, on the right, which is to redistribute the data among the partitions. So what you see on this picture is you have 4 partitions. So the bottom of the first stage is the map, and the top of the second stage is the groupBy. And so we're repartitioning from our 4 partitions, our 4 tasks, to another set of 4 tasks. By default, it's the same number, so that's why it's 4 to 4. Okay. And this repartitioning is simply a matter of hashing keys into buckets. So we hash like all of the A's into the same bucket, all of the B's in the same bucket, such that when we get to the groupBy, I can just look in one place and they'll all be there for sure. All right. Some optimizations to be aware of for the shuffle in general is that we try to avoid the shuffle whenever possible. If your data is already partitioned by the hash key, then we will not do the shuffle, and that's awesome. Secondly, we can use partial aggregation. In MapReduce, this is called map-side combine, where we actually reduce the amount of data we send by pre-aggregating it. For an example, word count, you can imagine instead of sending the word foo 100 times, you could just send, oh, I saw the word foo 100 times, and then you can just reduce the amount of data you actually send. In our particular case, we can't use either of these optimizations. In particular, like, we can't use partial aggregation because groupBy doesn't get reduced. Okay. So what I want to say is this is a nice picture. I want to go a little bit deeper into the shuffle because that's not exactly how it works. You'll note that what does it mean to, like, this looks like I'm pushing task, but I haven't even scheduled the task yet. I'm sitting here waiting to start stage 2. And so what actually happens is that the shuffle is not push-based, as the diagram kind of looks like. It's actually pull-based. And so in order to sort of make a very discrete boundary between the first and second stage, what we do is we actually write the intermediate files to disk, and then once the entire first stage is done, we'll start the second stage. So this first partition on stage 1 will, at the end, partition its own data to 4 files, such as this. So it does its own little hash key partitioning into these 4 files, and the others do the same. And so now we're left with a set of files. And then when we start the second stage, the first partition to the left will read from the first file of each of these partitions, like so. And that's how and thus it gets all its data by pulling from it, okay, et cetera. So I will note that this is actually, as of 1.1, which is not yet released, this is actually going to be a pluggable API. So this will be called the default shuffle implementation. And so hopefully we can have more specialized ones for that allow you to push, et cetera. Patrick already mentioned that, though. But if you're doing 1.0 today, this is how it will work. Okay, and this is how we move all-to-all data across the network whenever we have to do a shuffle. So now that we've gotten the data to the other side, the final thing to talk about here is how do we actually execute this groupBy. And this is beyond a groupBy. It's actually any sort of reduction. Like if you're doing a groupBy, for instance, what we do is we build a hash map for each of those partitions into memory, where the key is just whatever, and then the value is just sort of being appended along. So in this case, we have like A and all of the names that start with A, and E and all the names are starting with E. In the case of like a word count, you have like a word, comma, a value, and you just increment the value. Okay, so this is sort of how most like reductions will just work in Spark. One thing to know is that we can actually spill, and by spill I mean we can write to disk things across keys. So if you, I can spill like A to disk and then E to disk, but as a limitation of today's shuffle implementation that might bite you is that a single key value pair must fit in memory, and this is only really relevant for these large group bys with a single key very large. In this case, you'll note that my A has all of the names in my data set that start with A, not just the distinct ones, and so that can be actually very expensive. All right, and you'll note that we're actually done. That's all we needed to do. We've executed our stage 1, we've shuffled our data around, we know how to execute the group by, and now it's just a matter of scheduling these tasks for the stage 2 on our node. Okay, so first let's ask what went wrong in this specific example, and then let's generalize that. So what went wrong? We had too few partitions. We had 4 partitions and we only 3 machines, so we didn't really get good concurrency. We had a large per key group by, which could apply extra memory pressure, and we shipped all of the data across the cluster. We did a group by on all of the data. To generalize this a little bit, because I don't really care about this particular problem, I care about sort of the general ideas that we can get here. Here are some common issues I very commonly see people have, and sort of just to keep an eye on. So the first is ensure you have enough partitions. This is pretty obvious, right? If you have 20 cores, you need to make sure that you have at least 20 partitions, hopefully more than that, and I'll talk about more of that later. Minimize memory consumption. So in the case of sorting in large keys and group bys, remember we are bounded. These can use a lot of memory, and this can cause pressure, or potentially, in the worst case scenario, an out-of-memory error. Minimize the amount of data that you actually shuffle. In this case, we did a group by key with everything. That's pretty expensive. And this is actually kind of funny one. It's just know the standard library. Like a lot of problems can be avoided if you just like learn all of the functions in the library. It's not that big, and just so you get a sense of what you can do with the library and use the right function for the right place. 1 and 2. So I'm going to dig a little deeper into a couple of these. 1 and 2 here are about tuning the number of partitions. So let's talk about this. This actually comes up a lot. So when we talk about Spark, we actually need to think, not too much, but this is a pretty easy analysis, but we need to think about the number of partitions we have and we're working over. And so the first problem that you might run into is to have too few partitions, like we did in this example, and you have less concurrency than you might want. You're more susceptible to data skew. If you have, for instance, one task that's taking all of your time, then you're not getting much concurrency out of that. And finally, you actually have increased memory pressure for things like group by, reduce by key, and sort by key, even if they don't go out of memory, because like, as I said, our group by and our reduce by key, they can spill to disk. And as of version 1.1, sort by key will also be able to spill to disk. It'll be our last operation that is incapable of spilling to disk, fortunately. But as of 1.1, these things won't crash. However, they will increase the memory pressure, meaning that garbage collection problems become more of a big deal. And if your application is using more memory, then they can also be a bad time. A secondary issue is actually having too many partitions. This isn't too interesting. You'll see this very quickly when you see that it took way longer to schedule the tasks than it did to actually execute them, because it's executed in like 1 millisecond or something. So, all right, so what we need really is just a reasonable number of partitions. And so just to give you a very hand-wavy sense of what we see commonly, so you don't think that something is insane, is just very commonly we'll see between 100 and 10,000 partitions. Okay, so if you see like, oh, I think I need 1,000 partitions, that's a very reasonable number. You can go higher than 10,000 if you have a very large cluster or if you have a lot of data, and you go lower than 100 if you have a very small cluster or very small data. Okay, as a lower bound for a particular job, you tend to want at least 2 times as many cores as the number of clusters, as this number of cores in your cluster, perhaps a little less than that, so you can have like 2 waves at least. This allows you to have a little more wiggle room. And as sort of an upper bound, really the biggest upper bound in the number of tasks is the sort of the time. And so you want to ensure that tasks take at least, say, 100 milliseconds. If your tasks are in the range of seconds, you are probably experiencing almost no per partition, per task, or scheduling overhead. Although that is a little job dependent. All right, and so the last thing I want to address is memory problems, okay? Because I just want to be very straight here. I'm not trying to sell Spark to you. I'm trying to tell you how to get Spark to run well. So one thing that a lot of people come back and say, if they say that I can't get my job to run, most often they run into memory problems. And so the symptoms of memory problems, okay, actually let me talk a little more, one second before I get to that, before even diagnosing it. Memory problems stem from not so much the Spark core these days. As I said, almost all of our operators are able to spill to disk. But the problem is that Spark makes an assumption that it owns most of the memory. In fact, by default, the number is 90%. And so if because we allow you to write an arbitrary application user code inside of your job, and if your job assumes For instance, in the one we had here, we built a set in memory that can use a non-trivial amount of memory. And so really, if your amount of memory is getting very large, that can end up causing like serious problems, not just garbage collections, but actually out of memories. All right. And so how do I know I have a memory problem, first of all, so I can diagnose it? First of all, if you're seeing inexplicably bad performance, meaning that your task is running just fine and then suddenly the performance just hits a wall and it stops moving. Or if you're seeing inexplicable executor or machine failures, your machine just stops responding, not just a single machine that might have gone down, but many machines at once. And in fact, I've only seen inexplicable machine failures for two situations. One is heavy memory problems, where the kernel has stepped in and started killing things. And the second one is actually shuffles. If you have a very large shuffle, sometimes you'll exhaust the inode number. So that's just a little aside, in case you start running into that. But focusing more on the memory again, how do we make sure that we have a memory problem? Well, there's two executor Java options you can include. One is to have it print GC. What you'll see here is that the GC will start climbing, starting in like the seconds, and it might get to minutes, in fact, and sort of gets exponentially worse as the job can progress. Also, make sure you have heap dump on out-of-memory error, so that if it does die, you're guaranteed to see it and get a heap dump. Spark is actually good about telling you that you got an out-of-memory error. It should print it back to the executor, though, print it back to the driver. And finally, if you're really at a loss, you're looking at the executor log, and it just sort of stops. One thing that you might have to check is actually dmessage, which is the kernel level logging. And so you might see that the kernel's killer has stepped in and actually killed your process. All right, so these things are pretty good at letting you know that you have a memory problem. And so how do I resolve a memory problem? The final part. Well, first thing is obvious: increase the Spark executor memory, increase the amount of memory, the heap size of our executors. Second one is actually to increase the number of partitions. That can also be good, because as we said, larger partitions tend to mean more memory usage, which means, like, if I'm building a set in memory in my program from one partition, a smaller partition would strictly be better. So there's no reason that Spark doesn't need to say have a partition in memory. There's no, as of sort by key is again the last one, but as of sort by key, there's no reason that a whole partition has to ever fit in memory, or even a large part of it. But you can decrease the memory pressure by increasing the number of partitions. At some point, though, you may, this is a hard problem. If we allow you to execute arbitrary code and you can allocate arbitrary data structures, you may have to just reevaluate your program structure. Reevaluate to make sure that you are using an appropriate amount of memory such that one node can handle it. Each node can handle it. Not one node, each node. Each node can handle it, whatever it's allocated. All right, and this is a hard problem. I don't have a general solution for it, but at least hopefully we can figure it out when that's necessary. Okay. So let's go back to this example real quick and just try to fix our mistakes. And I don't really care too much about this example. What I really want to show is that we can sort of apply our four sort of common issues to this guy and see how we can change it. Let's see, how am I doing? OK, yeah. So I'm going to go through this very quickly because I actually wanted to show you a brief demo showing the differences here. So for instance, we can say that I need to ensure I have enough partitions for good concurrency. And so what I can do is throw in a repartition. This just takes my data, and without 4 parts, and makes it into 6. I can let's say, reduce memory consumption and reduce the shuffle by actually pushing the distinct up. And what I'm not trying to get here is that, first of all, this is a very specific example. Second of all, it's not easy to sort of say, oh, I should throw the distinct up there. Right? This is something that you have to sort of think about and do. But I'm just trying to show you how each one of these is sort of addressing one of the parts down there. And then if I do this distinct, I don't need to make that set, so I further reduce memory usage. And secondly, I can actually combine, I can reduce the data shuffle by combining the repartition shuffle, which does a shuffle by itself, and the distinct, which does a shuffle by itself, into a single operation, which is the distinct that does shuffle into 6 partitions. And finally, I can actually look at this group by key in names.size and see that this is actually a very common pattern in Spark. And there's a far more optimal way of doing it called reduce by key, which simply takes the key and applies this function to all the values. And now we see, by comparing this to our original, it's about the same number of lines of code. Maybe it looks even a little simpler. But certainly, if you approach this problem, or your coworker approached this problem, they might have very well come up with a second solution. And so the goal here isn't to understand how to go from one to the other. That sort of requires just thinking about your application. But the goal is to sort of be able to understand how the second one has better properties in terms of execution, in terms of the shuffle, in terms of memory usage than the second one. And now I actually want to show you this in action, if I can. demo gods be willing. Okay, let's see here. Okay, so this is, I mean, this is in our product because it's very nice to do demos in it. But what you'll see here is, this first one is the exact example we were looking at, except I replaced the HTTPS with S3. And there are 40 million names in this data set. There are 4 gzipped files. To show you my cluster, let me go over here. You'll see that I have, yes, indeed, I have 3 machines with 1 core each. I really stripped these machines down. And now I will execute this guy. All right, let's see if it starts running. Okay, it starts running. So let me just show you a little bit of detail by looking at the application. Sort of how can we look at the application and see maybe what's going on. Let's see here. Okay. So what we see here is it started executing the first stage. So remember, we have 2 stages in this guy. And the first stage is labeled here as the map stage. That's the last operation in the first stage. And maybe, and we see here also, we finished the first 3, and we just started the last task. So we can see that already there's some problems in terms of how we schedule these. So there's 2 waves, and it's not very even. And we see, OK, so I just refreshed. And so now the first stage has completed. The second stage has started. Again, it has this weird wave format. And we also see, looking at the right, the shuffle right, that we wrote 300 megabytes, which turns out is all of our data in a gzip format. And the other side, we're reading it, and we finished reading it. OK, so this whole thing took only about 41 seconds. But now let's try the better one, the one I just transformed. And let's try execute it. And we'll see this run. And we'll see that, so the bottom 2 are the previous ones, and the first one is the top. First one is the new one. And we'll see that it is starting out having only 3 guys execute. To give you a little clarity on what this is showing, actually, if you look at the task succeeded, there's a light blue section. And the light blue means what's currently running. The dark blue means what's finished. So we see that 3/4 of the bar is light blue, meaning that 3 tasks are finishing. And we can dig in deeper using this UI. I'm just starting the highest level. OK. So now it's already finished. So I can see that's finished back here. This one took 9 seconds. And the other one took approximately 41. So that's only about a 4x speedup. You can expect a 4 or 5x speedup. But you'll note that this is very small data. I've really trimmed this data down to just run in a few seconds to give a quick example. If this were like 40 minutes versus 10 minutes, you might start caring. And in fact, the first one scales much worse than the second one. So it might actually get worse than that. And so looking at the second one, these are the 3 stages. So this was actually divided up into more stages than the other one. But we actually wrote a lot less data. If you look at the far right column, the shuffle right column, we only wrote 155 kilobytes versus 300 megabytes. OK, so we were able to reduce the amount of shuffling. And after the first stage, you'll notice that we have 6 tasks in each. And so the data was executed through probably in 2 waves. OK, so we've sort of seen that some of the benefits we can get from optimizing. And we can see how we can use the UI, hopefully, to sort of see what's going wrong. And hopefully that's enough. So that's all I have. Thank you for your time. And
let me make a quick announcement, because we're going to add more time for questions. You should keep the mic. Hey, so we'll have plenty of time to have questions on this. Just wanted to make a quick announcement. It's 2:45 now. We're actually going to delay the start of the next session 15 minutes as we delayed this one. So we'll start at 3:15. And we'll let Aaron go over his time slot here a little bit, because I'm sure there will be questions. So thanks.
So the shuffle memory fraction? OK, so I mentioned earlier that Spark assumes it has 90% of them. Oh, yeah, sorry, my apologies. The question was, what is the shuffle memory fraction? And does Spark always write to disk? OK. Well, OK. So, and so the answer is that the shuffle memory fraction is by default 20%. And what that means is, for doing group bys, so try to be quiet if you're exiting or moving around to other places.
Could we collectively shush the crowd? Can we collectively shush here? Shh. Thank you. If you are going to leave, please leave quietly, because many people want to hear the answers to these questions. And just go talk outside. It's totally fine to do that. Thanks.
OK, thank you. So the shuffle memory fraction is 20% of the memory. And this is actually used not for the shuffle itself. This is used on the groupBy, like for the groupBy, the second side, the second stage of the shuffle. It's used to build this in-memory map. And so what this 20% means is it's willing to use 20% of total memory to build a map, and if it's going to go over that, it starts spilling to disk. Okay, so it starts spilling to disk. So that will use extra memory. The actual shuffle itself always does write to disk, although it will often hit buffer cache if you're not writing that much. So you don't have to worry about too high latencies until you start running a lot of data. Okay, question? So, okay. So the question was, how can we optimize the memory footprint of our RDDs? That's a pretty general question. I'm going to answer this in terms of caching. So when you load data from loaded data into an RDD, one thing that's sort of unexpected sometimes is sort of the fact that a deserialized object in memory is much, much larger than you might expect. Like a string is like twice as large. So one thing you can do if you're trying to keep a lot of data in memory is to cache it in a serialized fashion or to cache it off heap in something like Tachyon. And so a serialized fashion tends to be much more compressed. And you can actually set compression on for RDDs as like rdd.storage.compress or something like that to compress them in memory, and you can keep a very large amount of data in memory compared to having them deserialized. Hopefully that answers your question. Okay, so the question was, how do we decide, how can one sort of come up with a good number of reducers, and how can you assign them? So the number of reducers is by default the number of mappers. And this is, by the way, when I say reducers and mappers, it's the number of partitions in the first stage versus the second stage in any shuffle. It's by default the number of mappers, and this tends to be a pretty good default. You start running into problems when you have maybe like 1 million partitions, and you try to reduce to 1 million partitions, because that creates a lot of intermediate data. But in general, you follow the same rules as the number of mappers. You want enough partitions for concurrency, and maybe if you're doing a very large groupBy, you also want to have more reducers so that the data is more spread out among the partitions. What was the second question?
How the reducers are assigned.
Oh, how the reducers are assigned. I'm sorry. The reducers are assigned randomly because we read in the data from every. It's an all-to-all read anyway, so it doesn't really matter where we put the reducers. We just distribute them among the cluster. Question? Sorry, could you repeat your question? Oh, the last part.
So if I put that in a login, the distinct has actually run the combiner at the mapper side.
Yeah, so.
To the mapper side, right?
Sorry, I'm not sure I understand your question. Please.
How are we aggregating the data at the mapper side
Yeah.
to spill less data at the shuffle stage?
So if I understand your question, and if not, please come see me afterwards. If the question was, actually, I don't even know enough to answer the partial question. What happens on the map side? Well, okay, so on the map side of it, so maybe you're asking what on the map side of a distinct. Oh no, I see. Okay, sorry. Now I understand what your question was. How did we spill less data on the map side? Is I believe your question. So I had a distinct here, and then it turned out I spilled way less data to disk. And why is that true? If that's your question, that's a very good question. And the answer was this partial aggregation, because a distinct is actually just sort of a reduced by key where the value is always null, and you just, if you find two keys of the same value, two of the same key, you just put them in the same value, and so therefore you keep it distinct. And so it turned out there's a lot of distincts in the name database, and so we were able to only keep around on the map side the distinct names and write only those to disk. And so that's why it was much smaller than the 150 megabytes. Okay.
So is it like combining the values back to back for a particular key, or actually evaluating that to a one value also?
Are we combining the keys back to back? Yes, so we do combine the values for the same key in the map side, and then we do that. That's the partial aggregation, and then we do that again on the reduce side for all of the reduce keys. If that didn't answer your question, please come see me afterwards. Okay. Question.
Yeah, if you have a cluster that has heterogeneous nodes, so you've got half terabyte of something nodes in memory and only 128 gig of others, will Spark handle that gracefully, or is there something special you have to
So the question was, how does Spark handle it if you have a heterogeneous system where you have like a terabyte of memory on some machines and you like 120 gigabytes on other machines? Yes, Spark will handle this correctly insofar as as long as you tell Spark that each of these nodes have this much memory, which is specified on the worker itself, in a configuration, then Spark will not try to cache a terabyte on the 128 gigabyte nodes, for instance. And then so more data will become cached. One thing interesting about cache is a cache actually acts as data locality. So as more data gets cached in the 1 terabyte, you'll actually get more tasks executing on that one. So basically everything will work out perfectly well. Question?
So in previous talk, it says like you write once and run everywhere. So in your practice, it's like you have a hard-coded number of partitions. Is this kind of against the general practice over there?
So the question is having a hard-coded number of partitions. I see. To run in arbitrary scales. Yeah, I mean, if your idea is to write a job and then run it on a whole bunch of different clusters, you would not want to have a fixed number of partitions. You can get the total number of partitions, the number of cores in your system in Spark, and sort of by default, the default number of partitions is the number of cores in your system. And sort of you can sort of do like just a little bit of arithmetic on that and say that I want 2x or something. And this way, like just read the number for the current cluster and run on that, and that would allow you to be a little more versatile. Okay, so if you have a Spark application failure, also known as driver, there are two solutions to know like what went wrong. First of all, typically the driver runs like on a machine that you control, so you just run it and then like the application's running, so you can look at the logs there. Secondly, we just introduced in I believe 1.0 a history server, which allows you to see prior, like in the same way as like our Spark UI allows you to see like current executions. You can see prior ones, and you can look into there to see sort of previous, like to click on previous logs. That doesn't actually include the application logs though, because again, that's controlled by your own machine. So if you've lost those logs, there's not a lot we can do about that. Question?
Just follow up on that question. Suppose you're deployed a young cluster, how do you debug it?
Suppose you deploy a young cluster and you launch your
so your driver is not on your machine.
I see. Yeah, so you deploy, if a yarn cluster, you run your driver inside of the yarn cluster. I don't have actually a lot of experience running yarn clusters, but I imagine the logs go somewhere. and so the driver is a fixed point, so you'll have an IP. So basically, that's a fixed point you can go to look at the logs there, okay? So the driver logs are, like all of the executor logs, if you have an executor error or something, it'll be printed in the driver logs. So you only should have to find where the driver is.
But when the job finishes, the cluster is actually killed, so you don't have anything left.
When the job finishes, the cluster is killed, you have anything left? Well, I mean, if you're looking for the logs, you have to, the logs will still be there. I'm not sure what you're looking for, if not logs.
When you're starting young cluster, you actually start a container and then
Oh, okay, sure. So I see. So if the point is that the container is cleaned up after the job is finished and therefore you lose the logs, this would probably right now require a manual solution where you just upload the logs to S3 before completing the task or something like that.
There's also a depends on configuration.
Yeah, there's a configuration where it'll save the logs.
I apologize. It's actually even easier than that. There's a configuration already to save the logs somewhere else in a persistent storage. Thank you. All right, question. How do you force the shuffle files to go to tachyon? I'd like to say there's a way right now, but there's not currently a way. And the problem is our current shuffle implementation, it's now pluggable. So in 1.0, I'm saying there's not a way. After that, there'll be a way. But the problem is the current shuffle implementation uses the POSIX file system, so it can write to the local disk, it can write to an NFS disk, or it can write to like a RAM disk, but it can't write to an HDFS file system. So this would be something we'd love to do, but is not in 1.0 possible.
So you mentioned there shouldn't be a reason you need to bring an entire partition in memory anymore. What if you need to sort within a partition instead of a global sort by key?
Sort within a partition? That is what I see. Okay, so the question is, but sort by key does not group it by the key. It only sorts it by the key column. So it does do a global sort. So the question is, sort by key, doesn't that require loading in memory? And the answer is yes. Right now, it does require loading each partition in memory because we do it in memory sort. But there's a patch out right now which solves this problem. So it will not. A global sort will not require, in a similar way to mappers, it will not require everything to be in memory.
Actually, I didn't want a global sort. I just want to sort each partition.
Each partition. Oh, so, well, if you just want to sort each partition, but like within a partition, but well, so the standard library includes a way to do a global sort. If you don't care about the global part, well, we'll give it to you anyway. At this point. That's true. So you might have to do a okay. We don't have anything in the standard library, although I mean Spark. One thing that's nice about Spark is that you can sort of you can extract out what you want, and so you could use the same logic we use to do a global sort just to do the sort in a partition. It would require some manual work, but I don't think it'd be difficult. It's easy to do at the user level.
There are a few more questions.
Okay, maybe 2 or 3 more questions. Let's get from this half of the room.
So I have 2 questions in relation to Hadoop packages. Does Spark have something like a speculative
So the question is, does Spark have speculative execution? Yes, it does. It's actually not turned on by default, but just take a look at the configuration. You can just turn it on, and it'll execute when it's getting close to completion if there's tasks that are taking too long.
So in the case, like if you use speculative, would it make sense to have some number of partitions slightly less than the multiple of execution?
Yeah, so the question was, if when you use speculative execution, does it make sense to have slightly less than a multiple of the number of partitions? And yes, it does. So typically, I might say not actually 2x the number of cores, maybe a little bit less than 2x cores. I mean, you want to say something, Reynolds? Okay, so he gave me a weird look. But I would say that actually having a little less than 2x the number of cores is actually pretty good for wiggle room.
Yeah, our question is like, can you control like how many streams are merged at the same time and things like that?
Streams are merged?
In a large cluster, like during the reduce stage,
can you control the number of streams that are merged? That's not exactly how it works. Oh, I see. Yeah, that's not exactly how it works. So,
just comparing with
right, to compare, you don't have a control of the number of streams that are merged. Oh, okay. Yeah, Randall wants to make a clarification. In general, we don't really, like the number of partitions tends to be much greater than the number of cores. Like you might have 10,000 partitions for 64 cores, or for 100 cores or something. And so you don't often have to worry about the lower bound. Rather, many times you don't have to worry about the lower bound. You just have to make sure that it's at least there. One more question.
In the example you showed, it looked like the bytes written from the first stage was greater than the bytes read from the second stage. Can you explain that?
That's a great question, Patrick.
I can answer because we're wrapping up anyways.
Yeah.
Okay, I'll answer that because I'm going to wrap up anyways. So the reason why those metrics are different is that the question was we report the bytes written before a shuffle, and then we report the bytes read on the other side of the shuffle. And actually, it's almost always the case that the read bytes is strictly lower. And it's because we only count remote reads, so like reads from other nodes that are expensive. If a map outputs on the same node and then the reduce executes right there, it reads some fraction of the data set from the same node. So we don't report that because there's kind of no cost to doing that. But it's a common source of confusion, and there's been debate as to whether we should just sort of artificially report that as a read so that like it matches up and people don't get concerned. So that's the answer. But anyway, I didn't mean to interject here, so we should really give Aaron a huge round of applause.